Close your eyes and try to imagine infinity, not a really big number. Not billions or trillions, or even the number of atoms in the observable universe. Actual infinity, a number so large it never ends. That keeps going forever, no matter how long you count. Your brain can't do it. Evolution didn't prepare us for infinity. We evolved to track prey across savannas, to estimate distances to the next water source, to count members of our tribe. Our neural architecture is built for finite quantities, for numbers that end, for spaces that have boundaries. Yet cosmologists tell us the universe might be infinite, not just really big, actually infinite, extending forever in all directions, with no edge, no boundary, no place where space stops. And here's where things get disturbing. If the universe is truly infinite, with infinite space containing infinite matter, then everything that can happen must happen, not just once, infinitely many times. There must be infinite copies of Earth, infinite copies of you reading these words right now, infinite versions where you made different choices, where history unfolded differently, where everything that's possible has occurred. But when you look out at the night sky, you see a specific universe, particular patterns of galaxies, unique arrangements of matter. You don't see infinite versions of everything. You see one universe with one history. How can the universe be infinite yet also appear unique? How can infinite possibilities coexist with specific realities? This is the infinity paradox, and solving it requires understanding what infinity actually means in physics. If you're ready to descend into one of the deepest questions in cosmology, hit subscribe and prepare yourself. What you're about to discover will change how you think about existence itself. We begin. The question of whether the universe is infinite is not new. Ancient philosophers debated it. Medieval theologians argued about it. But for most of history, it remained purely philosophical speculation. No one could test the hypothesis. No observations could distinguish between infinite and merely very large. That changed in the 20th century. Einstein's general relativity provided a framework for describing the universe's geometry. The theory predicted that space could curve, that the universe could be finite, yet unbounded like the surface of a sphere, or it could be flat and infinite, like an endless plane. The question became measurable. By mapping the cosmic microwave background radiation, astronomers could determine the universe's curvature. If space curved positively, like a sphere's surface, the universe would be finite. If it curved negatively, like a saddle, it could be infinite. If it was perfectly flat, it was most likely infinite. The measurements came in starting in the early 2000s. The Wilkinson Microwave Anisotropy probe mapped the cosmic microwave background with unprecedented precision. The results were shocking. The universe is flat, not approximately flat, flat to within measurement error, which is less than 1% deviation from perfect flatness. A flat universe in general relativity is infinite. Space extends forever. There's no edge, no boundary, no place where you'd hit a wall or fall off an end. Go far enough in any direction and you'll keep going forever, never returning to your starting point, never finding anything resembling a limit. This created immediate philosophical problems. If the universe is infinite, and matter is distributed throughout it, then there must be infinite matter. Infinite galaxies, infinite stars, infinite planets. And if matter is distributed randomly, or according to quantum mechanical probabilities, then every possible arrangement of matter must occur somewhere. Not just possible arrangements that we'd consider likely. Every possible arrangement, no matter how improbable. Think about what this means. Somewhere in an infinite universe, there's a region of space where atoms happen to arrange themselves into an exact copy of Earth. Same continents, same oceans, same cities, same people. An identical copy of you reading identical words. The probability of this happening in any given region is incomprehensibly small. Take the number of atoms in Earth, roughly 10 to the power of 50. the number of possible arrangements of those atoms is unimaginably larger. The chance that random arrangement produces an exact copy of Earth is effectively zero. But multiply zero probability by infinite trials, and you get certainty. In an infinite universe, even impossibly unlikely events must occur. They must occur infinitely many times. There are infinite Earths out there, infinite copies of you, infinite versions where you made different choices, where history diverged, where everything played out differently. This is called the infinite duplicate problem, and it's one of the strangest predictions of modern cosmology. It's not speculation or science fiction. It's a logical consequence of the universe being infinite and matter being distributed according to known physics. But here's what makes the paradox sharp. You experience one reality. You made specific choices. History followed one path. The universe around you has a particular arrangement. You don't see infinite versions, you see one. How can both be true? How can infinite copies exist while you experience uniqueness? Some physicists argue the resolution lies in the speed of light and the expansion of space. Yes, infinite copies exist, but they're so far away their light will never reach us. They exist in regions of space that are causally disconnected from us, separated by distances so vast that no signal or information can ever travel between us and them. Think of the universe as an infinite ocean. You float on a raft with a horizon. Everything within your horizon, everything you can possibly see or interact with, is finite. But beyond that horizon lies more ocean, more rafts, more horizons. The ocean is infinite, but your observable universe is finite. This preserves uniqueness in a practical sense. Within our observable universe, our 93 billion light-year diameter bubble, we might be unique. Earth might be the only Earth. You might be the only you. The infinite copies exist beyond our cosmic horizon, where we can never observe them or interact with them. But this solution creates new problems. If infinite copies exist beyond our horizon, then physics can never make unique predictions. For every possible outcome of an event, there's a region of the infinite universe where that outcome occurred. The universe doesn't select one possibility, it realizes all of them. This challenges the very nature of scientific prediction. Science succeeds by predicting what will happen. But in an infinite universe, everything that can happen does happen somewhere. Prediction becomes meaningless when all possibilities are realized. Some cosmologists respond by rejecting infinity. They argue the universe might be finite after all, just very large enough to appear flat within our measurement precision, but ultimately closed and bounded. This would solve the infinite duplicate problem by making the universe finite, allowing for uniqueness without paradox. Others embrace infinity and its strange consequences. They argue we must accept what observations tell us, even if it violates intuition. The universe is flat. Flat universes in general relativity are infinite. We must deal with the implications, however uncomfortable they make us. A third group questions whether the universe being spatially infinite necessarily implies infinite duplicates. Perhaps matter isn't infinite even if space is. Perhaps the universe becomes empty beyond some enormous but finite distance. Perhaps some mechanism prevents matter from existing infinitely far away. These debates aren't settled. They represent the frontier of cosmology, where observations meet philosophy, where measurements confront the limits of comprehension. What we know for certain is this: the universe appears flat. In standard cosmology, this suggests infinity, and infinity creates paradoxes we haven't fully resolved. The question isn't just whether the universe is infinite, it's what infinity means for existence, for uniqueness, for the nature of reality itself. It's asking whether the universe is stranger than we can imagine, or whether our intuitions about infinity mislead us. Over the next sections, we'll explore these questions from multiple angles. We'll examine what observations really tell us about the universe's size, We'll investigate whether infinity necessarily implies duplication. We'll consider alternatives to the standard picture and their implications. The infinity paradox challenges everything we think we understand about the cosmos, and solving it might reveal truths stranger than the paradox itself. How do you measure infinity? The question sounds nonsensical. By definition, infinity has no measure, no size, no quantity you can determine. It's unlimited, boundless, beyond measurement. Yet cosmologists claim to have evidence the universe might be infinite. They base this on measurements, on data, on observations of the cosmic microwave background and galaxy distributions. How can you measure the unmeasurable? The answer involves a subtle distinction. You can't measure the universe's total size, but you can measure its curvature. And curvature determines whether the universe is infinite or finite. Think of the surface of a sphere. It's finite in area, but has no edges or boundaries. An ant walking on a sphere would never find an end. It could walk forever and never fall off or hit a wall. Yet the sphere's surface has a specific finite area you can calculate from its radius. Now imagine the surface of a perfectly flat plane extending forever in all directions. This surface is infinite. There's no total area. An ant could walk forever and never return to its starting point or find an edge. The key difference is curvature. The sphere has positive curvature. At every point, the surface curves inward. The plane has zero curvature. At every point, it's perfectly flat. Our universe might be three-dimensional, but the same geometric principles apply. If space has positive curvature, curving back on itself in 4 dimensions, the way a sphere's surface curves in 3, then the universe is finite. It has a specific volume, even though it has no edges. If space has negative curvature, like a saddle shape extended to 3 dimensions, the universe could be infinite. If space is perfectly flat, with zero curvature, it's almost certainly infinite. Measuring curvature requires looking at the largest structures we can observe. Small regions of space might appear flat, even if the universe as a whole curves. You need to measure cosmic scale geometry. The cosmic microwave background provides this measurement. This radiation, released 380,000 years after the Big Bang, comes from the most distant observable region of space. It carries information about the universe's geometry, encoded in the pattern of temperature fluctuations across the sky. Here's how it works. In the early universe, matter and radiation formed a hot plasma. Sound waves traveled through this plasma, creating regions of higher and lower density. These sound waves had a characteristic wavelength determined by the physics of the early universe. When the universe cooled enough for atoms to form, the plasma became transparent. The sound waves froze into the pattern we observe today as temperature fluctuations in the cosmic microwave background. The angular size of these fluctuations depends on the universe's curvature. In a positively curved universe, space acts like a lens, making fluctuations appear larger than they would in flat space. In a negatively curved universe, they appear smaller. In flat space, they have a specific, predictable size. The Wilkinson microwave anisotropy probe measured this angular size with extraordinary precision. Later, the Planck satellite improved the measurements further. The results were unambiguous. The fluctuations have exactly the size expected for a flat universe. Within measurement uncertainty of less than 0.5%, the universe's curvature is 0. This is remarkable because there's no reason the universe should be flat. It could have any amount of positive or negative curvature. The fact that it's flat to high precision demands explanation. Cosmic inflation provides that explanation. This theory proposes that the universe underwent exponential expansion in its first fraction of a second. This expansion stretched space so dramatically that any initial curvature was diluted away, leaving the universe nearly perfectly flat. Think of inflating a balloon. The balloon's surface has positive curvature. But if you inflated it to the size of the observable universe, any small region would appear perfectly flat. The curvature would be diluted to unmeasurable levels. Inflation predicts flatness. Observations confirm flatness. This counts as evidence for inflation and for the conclusion that the universe is infinite. But there's a subtlety here that cosmologists sometimes overlook when explaining to the public. Flat doesn't necessarily mean infinite. A flat universe is infinite only if it's simply connected, meaning there are no topological tricks that allow space to loop back on itself. Imagine a flat piece of paper. It extends infinitely in 2 dimensions. But now imagine taking the paper and connecting opposite edges, forming a cylinder. The surface of this cylinder is still flat locally. An ant crawling on it would never detect curvature, but the cylinder is finite. The ant would eventually return to its starting point. You could do more complex topology tricks, connecting edges in different ways, creating a torus, or more exotic shapes. All of these would be flat locally, but finite globally. Could the universe have such topology? Could space be flat, yet loop back on itself in ways that make it finite? Astronomers have searched for evidence of this. If the universe wrapped around, you might see multiple images of the same distant galaxies, light that travelled different paths around the universe to reach us from different directions. No such repeating patterns have been found. The observable universe shows no signs of topological identification. Every galaxy appears unique. This suggests the universe either doesn't loop back on itself or loops on scales much larger than the observable universe. If it loops on scales larger than observable, then it's effectively infinite for us. We'll never detect the looping. We'll never see the edge. For all practical purposes, the universe is infinite. This brings us to another crucial point. We can only observe a finite region. Light travels at finite speed. The universe has finite age. This means light has only had 13.8 billion years to reach us. Actually, due to cosmic expansion, we can see objects that are now 46.5 billion light-years away in any direction, giving us an observable universe 93 billion light-years in diameter. Beyond that distance lies the unobservable universe. Light from those regions hasn't had time to reach us yet. We can't see what's there, we can't measure it. We can't determine directly whether it's finite or infinite. All our measurements tell us about the observable universe. When we say the universe is flat, we mean the observable universe is flat. We extrapolate to conclude the whole universe is probably infinite, but this is inference, not direct measurement. And here's where things get philosophically tricky. If regions exist that we can never observe, do they have physical reality? Can science make statements about things that are fundamentally unobservable? This touches on deep questions about the nature of scientific knowledge. Some philosophers argue that science should restrict itself to observable phenomena. Making claims about unobservable regions is metaphysics, not physics. Others counter that extrapolation is fundamental to science. We observe that gravity works the same way in distant galaxies as it does on Earth. We extrapolate that physical laws are universal. Similarly, if space is flat here, we extrapolate it's flat everywhere. The infinity question highlights tension between these views. We measure flatness in the observable universe. We infer infinity for the whole universe, but we can never verify that infinity directly. Moreover, future observations won't help. As the universe expands and ages, the observable universe grows larger. We see more distant regions as their light reaches us. But the unobservable universe always remains beyond our horizon. The gap between what we can see and what might exist never closes. We're like observers trapped on an island, trying to determine if the ocean is infinite by measuring the curvature of Earth's surface. We can make good inferences, but we can never see the infinite ocean directly if it exists. This doesn't mean the question is meaningless. It means we must be careful about what we claim to know versus what we infer. The observable universe is flat. This suggests, under standard assumptions, that the total universe is infinite. But the suggestion isn't certainty, and the assumptions might be wrong. Cosmology operates at the boundary of the knowable. The infinity question shows us that boundary clearly. We've measured what we can measure. We've pushed observations to their limits, and we've reached a conclusion that remains forever beyond direct verification. The universe might be infinite. Our best measurements suggest it is. But proving infinity is impossible, and alternatives remain that could preserve finitude while matching all observations. Stand outside on a clear night and look up. You're seeing light from stars and galaxies scattered across billions of light years. Each photon travelled through space for vast amounts of time to reach your eyes. The farther away an object is, the longer its light took to arrive, and the further back in time you're seeing. Now here's what should disturb you. The most distant objects you can observe in opposite directions of the sky have never been in contact with each other. Light from one has never reached the other. They've never exchanged information. They've never interacted causally in any way. Yet when you measure their properties, they're remarkably similar. The temperature of the cosmic microwave background is the same in all directions, to 1 part in 100,000. The density of matter is uniform. The laws of physics work identically. How can regions that have never communicated be so similar? This is the horizon problem, and it becomes especially acute if the universe is infinite. Let's trace the logic carefully. The universe is 13.8 billion years old. Light travels at finite speed. This means any region of space has a cosmic horizon beyond which no signal could have reached it since the Big Bang. Your cosmic horizon sits 46.5 billion light-years away in all directions, creating an observable sphere 93 billion light-years across. This is the region you could possibly have influenced or been influenced by, given the universe's age and light speed. Everything beyond your horizon lies in the unobservable universe. You've never received information from there. You've never sent information there. The region is causally disconnected from you. Now consider 2 points in opposite directions near the edge of your observable universe. They're separated by 93 billion light-years. Light travelling between them would need 93 billion years to cross that distance. But the universe is only 13.8 billion years old. These 2 points have never been in causal contact. No signal could have travelled between them. They've never exchanged information, yet they have nearly identical properties. Both regions have the same temperature cosmic microwave background radiation. Both have similar densities of matter and dark matter. Both appear to follow the same physical laws. How is this possible if they've never communicated? You might think the answer is that they started with similar properties at the Big Bang, but this just pushes the mystery back one step. Why would the initial conditions be so similar across regions that had never been in contact? In fact, the problem is worse in the early universe. As you go back in time toward the Big Bang, the horizon distance shrinks. At the moment the cosmic microwave background was released, 380,000 years after the Big Bang, the horizon was much smaller. Calculations show that the observable universe at that time consisted of about 100,000 causally disconnected regions. These regions had never been in contact. They couldn't have exchanged information. Yet they all had the same temperature to extraordinary precision. It's like discovering 100,000 people scattered across the globe who've never met, never communicated, never even heard of each other, and finding they're all wearing identical clothes, speaking identical languages, following identical customs. The coincidence strains credibility. If the universe is infinite, the problem becomes infinitely worse. An infinite universe contains infinitely many regions beyond each other's horizons. These regions have no causal connection whatsoever. Yet observations suggest uniformity extends far beyond our observable universe. Wherever we look, the universe appears similar. How can infinite regions that have never communicated all have the same properties? The standard answer is cosmic inflation. This theory proposes that the universe underwent exponential expansion in its first 10 to the power of minus 32 seconds. During this tiny interval, space expanded by a factor of at least 10 to the power of 26. Before inflation, the entire observable universe was compressed into a region so small that all its parts were in causal contact. They could communicate, they could equilibrate to the same temperature and density. They started with uniform properties because they had time to smooth out any irregularities. Then inflation stretched this tiny uniform region to enormous size, larger than our current observable universe. Regions that were once in contact became separated by vast distances, pushed apart by the exponential expansion faster than light could travel between them. This explains the uniformity. All the regions we see came from the same tiny initial patch. They started uniform because they had time to interact before inflation separated them. Think of filling a balloon with air from a single source. The air starts in one small region with uniform temperature and pressure. Then you rapidly inflate the balloon. Parts of the balloon's surface that were close together are now far apart, but they all contain air from the same source with the same properties. Inflation solves the horizon problem elegantly. It explains why causally disconnected regions have similar properties. They weren't always disconnected. Inflation created the disconnection by expanding space faster than light could travel. But inflation also makes the infinity problem worse in a peculiar way. If inflation happened, it probably created a universe far larger than the observable portion. Most inflation models predict the total universe is exponentially larger than what we can see, possibly infinite, even if it started finite. Moreover, in many inflation models, inflation never completely stops. It ends in some regions, creating pocket universes like ours where normal expansion takes over. But in other regions, inflation continues, creating more space that eventually spawns more pocket universes. This eternal inflation scenario suggests an infinite multiverse of pocket universes, each with potentially different properties, all embedded in an eternally inflating background space. If eternal inflation is correct, then not only is our universe infinite, but it's one of infinitely many universes in an infinite multiverse. The infinity problem multiplies into an infinity of infinity problems. And here's where philosophical concerns become acute. If infinitely many pocket universes exist with all possible properties, then physics can't predict what we'll observe. Every possible outcome occurs somewhere. The theory becomes unfalsifiable because it predicts everything. Some cosmologists embrace this, arguing we must accept what inflation models predict, even if it challenges traditional notions of scientific prediction. Others reject eternal inflation precisely because of these implications, arguing theories that predict everything predict nothing. The horizon problem also connects to the question of whether everything exists everywhere in an infinite universe. If the universe is truly infinite and uniform, then beyond our horizon lie regions statistically identical to our observable universe. Go far enough and you'll find another region with the same distribution of galaxies, same structure formation history, eventually even the same atomic arrangements. The horizon problem initially appears as a mystery about why separated regions are similar, but in an infinite uniform universe, it becomes a statement about infinite repetition. The regions are similar because similar conditions lead to similar outcomes, and in infinity, all conditions repeat. This brings us back to the original paradox. We observe uniformity suggesting infinity, but infinity implies infinite duplication, yet we experience uniqueness. The horizon problem shows us both sides of the paradox, the evidence for infinity and the strangeness it creates. Solving the horizon problem with inflation creates new infinities. These infinities explain observations, but challenge comprehension. We're left asking whether we've truly solved the mystery or simply replaced one infinity paradox with another. The cosmic horizon limits what we can observe, but it doesn't limit what exists. Beyond our horizon, the universe continues. Whether it's finite or infinite, uniform or diverse, unique or endlessly duplicated, we can't directly determine. We're trapped inside our horizon, looking out at a finite window on what might be infinite reality. The horizon problem reminds us of this limitation, while simultaneously providing clues about what lies beyond. The paradox of infinity gets stranger when you add quantum mechanics. Not because quantum mechanics solves the problem, but because it adds new layers of infinity that make everything even more confusing. In classical physics, the universe has a definite state. Every particle has a specific position and momentum. Every field has particular values. The universe follows one history, one sequence of events, from past to future. If you could know the state precisely at any moment, you could, in principle, calculate all past and future states. Quantum mechanics shatters this picture. Particles don't have definite positions until measured. They exist in superpositions, simultaneously occupying multiple states. The universe doesn't follow one history, but evolves according to a wave function that encompasses all possible histories simultaneously. When you make a measurement, the wave function appears to collapse. Possibilities become actualities. The particle that was everywhere is now somewhere. The universe that contained multiple potential futures realizes one specific future. But here's the disturbing question that's haunted quantum mechanics since its inception. What happens to the other possibilities? The Copenhagen interpretation says they simply cease to exist. The wave function collapses real. Measurement creates reality by selecting one outcome from many possibilities. The other outcomes weren't real, they were just mathematical representations of potential. But an alternative interpretation exists that takes the wave function completely literally. The many worlds interpretation says all possible outcomes actually occur when you measure a particle's position and find it at location A. There's another version of you that measured it at location B, and another at location C, and so on, for every possible measurement outcome. The universe doesn't select one possibility. It realizes all of them in separate branches. Reality splits at every quantum event, creating a vast tree of parallel worlds where all possible histories play out. If many worlds is correct, then the universe is infinite, not just in space, but in possibility. Even if space were finite, the number of parallel branches would be infinite. Every quantum event creates new branches, and quantum events happen constantly throughout the universe. This creates a different kind of infinity than spatial infinity. You don't need to travel anywhere to reach these other branches. They coexist with you, occupying the same space but evolving along different branches of the universal wave function. Think about what this means for personal identity. Right now, as you read these words, quantum events are occurring in your brain. Electrons tunneling through barriers, ions crossing membranes, quantum processes at the molecular level that influence neural activity. In many worlds, each possible outcome of these quantum events creates a new branch. There are versions of you where different quantum events occurred, leading to slightly different thoughts, slightly different neural patterns, eventually diverging into meaningfully different lives and choices. How many branches are there? The number is staggeringly large, possibly infinite. Every quantum event throughout cosmic history spawns new branches. The number grows exponentially, with time and with the number of particles in the universe. If the universe is also spatially infinite, you get infinity multiplied by infinity. Infinite space creates infinite spatial duplicates of you. Many worlds creates infinite quantum duplicates. Together, they create an incomprehensibly vast ensemble of versions of you, living out every possible variation of your life. This makes the original infinity paradox even more acute. Not only might there be spatial copies of you elsewhere in an infinite universe, there are quantum copies in parallel branches right here. You are not one person having one experience. You're a vast collection of versions experiencing all possibilities. Yet you experience one reality. You made specific choices. You observe specific outcomes. You don't see or experience the other branches. How can you be one version among infinite versions, yet have no access to or awareness of the others? Many worlds advocates argue this isn't a problem. Each branch is real and complete. You exist in one branch experiencing that branch's reality. Other versions of you exist in other branches experiencing those realities. There's no paradox because the branches don't interact, but this creates problems for probability. Quantum mechanics makes probabilistic predictions. It says outcome A occurs with 70% probability and outcome B with 30% probability. But in many worlds, both outcomes occur with certainty in different branches. What does probability mean if all outcomes happen? The standard answer invokes the Born rule, a mathematical formula that tells you how to assign probabilities to branches. But deriving the Born rule from the many worlds framework remains controversial. Some physicists argue it's been solved, others insist it remains a fatal flaw in the interpretation. There's also the question of what constitutes a branch. When exactly does the universe split? At every quantum event? At every possible quantum event? Do macroscopic objects split, or only quantum systems? Where do you draw the line between quantum and classical behavior? These questions don't have agreed upon answers. Different versions of many worlds handle them differently. This makes testing the interpretation difficult because its predictions depend on how you formalize it. Now combine many worlds with spatial infinity. Somewhere in an infinite universe, there's a region where quantum events happened to evolve in exactly the same way they did here. A spatial duplicate where all the quantum branches match our branches, creating a perfect copy not just of matter arrangement, but of quantum history. This duplicate would be indistinguishable from our region, not just in terms of atoms and molecules, but in terms of which branch of the quantum wave function realized here and there. It would have the same history, same quantum outcomes, same experiential reality. How far away is such a duplicate? The number is incomprehensibly large. The probability of quantum histories matching decreases exponentially with the number of quantum events. For all the quantum events in Earth's history, the probability is so small that the distance to a duplicate exceeds what we can write in any reasonable notation. But in an infinite universe, that duplicate exists. In fact, infinite duplicates exist, each with matching quantum histories. This creates a strange kind of determinism. In any finite region, quantum mechanics introduces genuine randomness. Outcomes are unpredictable. The future is open. But in an infinite universe with many worlds, all possible quantum histories occur somewhere. The ensemble is deterministic, even though individual branches are random. Some physicists find this comforting. It means the universe as a whole is deterministic and complete. All possibilities are realized. Nothing is left out. The appearance of randomness is just our limited perspective within one branch. Others find it deeply troubling. If all possibilities occur, then free will becomes questionable. Your choices don't determine outcomes because all possible outcomes occur in different branches. Decision-making becomes meaningless when all choices are made by different versions of you. The infinity problem in quantum mechanics also affects how we think about the universe's origin. If many worlds is correct, the Big Bang wasn't a single event. It was a branching point where infinitely many possible early universes diverged. Each branch evolved according to slightly different quantum outcomes in the early universe. Most branches are probably very different from ours, but somewhere in the infinite tree of possibilities, many branches look like our universe because the quantum randomness happened to produce similar outcomes. This means our universe isn't unique, even in its history. It's one branch among infinitely many, distinguished only by the particular sequence of quantum events that occurred here, but not by any fundamental difference from other branches. The combination of spatial infinity and quantum infinity creates a picture of reality so vast it defies comprehension. You're not just one person in one universe, you're one version of one person in one branch of one region of an infinite multiverse where every possibility plays out infinitely many times. Yet you experience one reality, one life, one sequence of events. You don't feel the infinities. You don't see the branches. You exist as if you're unique, even though the mathematics suggests you're infinitely replicated. How do we reconcile this? How do we make sense of being one among infinite many? How do we think about choice, meaning, and identity when everything that can happen does happen? These aren't just abstract philosophical questions. They're practical issues that arise when you take infinity seriously in both spatial and quantum contexts. And they're questions that physics alone might not be able to answer. Here's a disturbing thought experiment. Right now, as you read these words, your memories of the past, your sense of having a continuous existence, your entire experiential history, all of it is encoded in the physical state of your brain. Neurons firing in particular patterns, molecules arranged in specific configurations, electrical and chemical activity creating your conscious experience of being you. Now ask yourself, how do you know your memories are real? How do you know you didn't spontaneously form 1 second ago with all your memories already in place, making you think you've existed for years when you've actually only existed for a moment? You can't prove you didn't. All the evidence you'd cite, your memories, your experiences, your sense of continuous existence, all of it would be exactly the same whether you've really existed for years or just appeared 1 second ago with fake memories. This might seem like pointless philosophical skepticism. Obviously, you've existed for more than 1 second. Obviously, your memories are real. But in an infinite universe, the question becomes more than philosophical. It becomes a statistical prediction that might be wrong. The problem is called Boltzmann brains, named after Ludwig Boltzmann, who identified similar issues in 19th century statistical mechanics. The logic is simple and devastating. In an infinite universe, or even just a very large finite universe, quantum fluctuations constantly create and destroy matter. These fluctuations are normally tiny, creating and destroying a few particles before disappearing. But given enough time and space, larger fluctuations can occur. Most fluctuations remain small because larger fluctuations are exponentially less probable. But improbability isn't impossibility. In infinite time or infinite space, even fantastically improbable events occur. Now consider 2 ways you could exist. The normal way, the universe starts with a big bang, forms galaxies and stars, creates Earth, life evolves for billions of years, and eventually you're born and develop normally over decades. Or the Boltzmann way, quantum fluctuations spontaneously arrange atoms into a brain identical to yours, complete with all your memories and thoughts, existing for just a moment before dissolving back into chaos. Which is more probable? The normal way requires the entire history of the universe to unfold correctly over billions of years. Countless events had to happen in precise sequence. Stars had to form, Earth had to exist, evolution had to follow a particular path. Your parents had to meet. An inconceivably complex chain of events led to you. The Boltzmann way requires just one quantum fluctuation, admittedly an extremely improbable one, but still just one event. No history needed, no evolution, No universe full of structure, just a random fluctuation that happens to create a brain with your exact mental state. The Boltzmann brain is vastly more probable than normal formation because it requires vastly less structure. Creating just a brain is easier than creating an entire universe. In an infinite universe, both happen infinitely often. But the ratio matters. If Boltzmann brains outnumber normal brains, then statistically, you're probably a Boltzmann brain. Your memories are false. You just appeared this instant and will dissolve the next. This seems absurd. Obviously, you're not a Boltzmann brain. You have genuine history, real memories, continuous existence. But can you prove it? Can you provide any evidence that distinguishes between being normal you versus Boltzmann you? Every piece of evidence you'd cite, every memory, every experience is identical in both scenarios. There's no way to tell the difference from the inside. This is where infinity creates genuine problems for physics. If most observers in the universe are Boltzmann brains, then our experiences and observations can't be trusted. We think we see an orderly universe governed by physical laws, but that perception might be a random fluctuation that will dissolve momentarily. Science requires that observations reflect genuine reality. If most observations come from Boltzmann brains experiencing false realities, then science breaks down. You can't learn about the universe through observation if observations are mostly hallucinations from fluctuating brains. Some cosmological models predict that Boltzmann brains do outnumber normal observers, and this is considered a fatal flaw in those models. A theory that predicts your experiences are most likely false is a theory that undermines itself. If the theory is true, you can't trust your observations that led you to believe the theory in the first place. This criterion, avoiding Boltzmann brain domination, has become a test for cosmological theories. Models must predict that normal observers vastly outnumber Boltzmann brains, or they're rejected as inconsistent. But this creates tension with infinity. In an infinite universe, both types of observers exist infinitely. Comparing infinities is mathematically problematic. You can't simply ask which infinity is bigger, because infinite sets don't work that way. You need a measure, a way of assigning probabilities to infinite sets. Different measures give different answers about which type of observer is more common, and there's no agreed upon way to choose the correct measure. This is the cosmological measure problem. In finite universes, you count observers and compute ratios. In infinite universes, you need a prescription for how to compare infinite quantities, and different prescriptions give different predictions. Some measures predict Boltzmann brains dominate. Others predict normal observers dominate. The choice of measure determines the theory's predictions, but we have no empirical way to determine which measure is correct. Think of trying to compare the number of even integers versus odd integers. Both sets are infinite. Which is larger? The question seems meaningless, because for every even number, there's a corresponding odd number. The sets have the same cardinality. But what if you count differently? What if you count all numbers from 1 to n, and then take the limit as n approaches infinity? Now the ratio of evens to odds depends on whether n is even or odd. The infinity's size depends on how you approach it. Cosmological measures face similar ambiguities. The answer to, are you probably a Boltzmann brain, depends on how you define probability in an infinite universe, and that definition is arbitrary. This deeply troubles some physicists. Science should make definite predictions, but infinity, combined with quantum mechanics, seems to create ambiguity at the most fundamental level. Different equally valid mathematical approaches give different answers about physical reality. Others argue this shows infinity might not be physical. Maybe the universe is actually finite, but very large enough to appear infinite within measurement precision, but actually finite, avoiding the mathematical pathologies of true infinity. But making the universe finite doesn't automatically solve the problem. In a finite but very large universe that exists for very long times, Boltzmann brains can still outnumber normal observers. The problem shifts from infinity to large finite numbers, but the pathology remains. The resolution might involve the cosmological constant and dark energy. Our universe has a positive cosmological constant, causing accelerated expansion. This expansion creates a cosmic horizon beyond which we can never observe. In universes with cosmic horizons, the observable region has finite volume bounded by the horizon. Even if space extends infinitely beyond the horizon, each observer has access to only finite volume. This finiteness might be enough to avoid Boltzmann brain problems. The math works roughly like this. In our observable universe, normal observers formed through cosmic evolution vastly outnumber any Boltzmann brains that might fluctuate into existence. The time available before expansion carries matter beyond our horizon is finite, limiting how many fluctuations can occur within our causal patch. So, within our observable universe, we're safe. Normal observers dominate. The Boltzmann brain problem is solved practically even if infinity creates theoretical ambiguities beyond our horizon. But this solution only works if the cosmological constant remains positive forever. If it decays to zero or goes negative, the horizon disappears, time becomes infinite, and Boltzmann brains eventually dominate again in the far future. We don't know whether the cosmological constant is truly constant. It might evolve. If it does, the Boltzmann brain problem might return, just delayed billions or trillions of years. The problem also raises questions about personal identity and existence. If you're statistically more likely to be a Boltzmann brain than a normal observer, what does that say about the nature of consciousness? It suggests consciousness doesn't require genuine history. A brain with fake memories experiences consciousness just as vividly as one with real memories. The subjective experience is identical, even though the objective reality differs completely. This implies consciousness is a pattern, not a history. You are what your brain is doing now, not what it did in the past. Memory creates the illusion of continuous existence, but the continuity might be false without changing the experience. Some philosophers embrace this, arguing it reveals deep truths about consciousness and identity. Others recoil, insisting it proves something has gone wrong in our cosmological reasoning. The Boltzmann brain problem is where infinity meets consciousness in the most disturbing possible way. It takes abstract questions about infinite universes and makes them personal. It's not just asking whether infinite copies of you exist somewhere. It's asking whether the you reading these words right now is real or a fluctuation. And the disturbing part is that you can't know. There's no test, no observation, no evidence that distinguishes between the possibilities from your perspective. The Boltzmann brain thinks and feels exactly the same as the real brain because it's identical in structure. This is why most cosmologists reject theories that predict Boltzmann brain dominance, not because they've proven such theories are wrong, but because accepting them would undermine the entire scientific enterprise. Science requires trust in observations. If observations mostly come from fluctuating brains with false perceptions, science becomes impossible. We assume we're normal observers with genuine history because we must. Without that assumption, nothing else makes sense. But the assumption is just that, an assumption, not something we can prove from first principles. Infinity forces us to confront these assumptions explicitly. In finite universes, we can avoid the question, but infinity brings it to the surface, making us acknowledge that our confidence in reality's coherence rests on assumptions about measure and probability in infinite sets. The Boltzmann brain problem isn't solved. It's avoided in specific cosmological models through particular assumptions about how probability works in infinite or very large universes. But the underlying tension remains, waiting to resurface whenever we consider the implications of infinity seriously. Let's return to the original disturbing implication of infinity. If the universe is infinite and matter is distributed throughout it, then everything that can happen must happen, not just once, infinitely many times. There are infinite copies of Earth, infinite copies of you, infinite versions where history diverged at various points, infinite variants living out every possible life you could have lived. This isn't speculation. It's a straightforward consequence of infinity combined with finite configurations. The number of ways to arrange atoms in a region of space is vast but finite. In infinite space, every possible arrangement must occur infinitely often. Let's work through the math roughly. Take a sphere 1 billion light years in radius. Count the number of atoms inside it, approximately 10 to the power of 80. These atoms could be arranged in many ways, but the number of arrangements is finite. How many arrangements? It's an incomprehensibly large number, but it's not infinite. Call it n. In an infinite universe with matter distributed throughout, that sphere-sized region of space will be duplicated. Every one of the n possible arrangements occurs somewhere. More than that, each arrangement occurs infinitely many times. In infinite space, you can fit infinitely many non-overlapping spheres of any finite size. Each sphere has one of the n possible arrangements. With infinitely many spheres and only n arrangements, each arrangement must repeat infinitely. This means somewhere, roughly 10 to the power of 80 meters away. According to some estimates, there's another region identical to our observable universe. Same galaxies, same stars, same Earth, same you reading the same words. The distance is incomprehensibly vast. Light would take longer than the 10 to the power of 80 years to travel there, a number so large it exceeds the current age of the universe by factors that defy description. You'll never observe these duplicates. No signal from them will ever reach you. They're beyond any possible causal contact. But they exist if the universe is infinite and matter fills it. This is mathematical certainty, not speculation. Now ask yourself, what makes you you? Is it your physical composition, the specific arrangement of atoms in your body and brain, or is it something else, some non-physical essence that distinguishes you from duplicates? If you're materialist, believing consciousness emerges from physical arrangements of matter, then your duplicates are you. They're not copies in the sense of being similar, but distinct. They're identical to you in every physical sense. They have the same thoughts, same memories, same experiences at the moment of duplication. Which one is the real you? The question seems meaningless. Both are equally real. Both experience themselves as unique individuals. Both would deny being duplicates because neither has access to the other. From your subjective experience, you're unique, but objectively, in an infinite universe, you're one instance of a pattern that repeats infinitely. Your uniqueness is local, not global. Within your observable universe, you're unique. In the infinite totality, you're replicated endlessly. This challenges intuitions about identity. We think of ourselves as individuals, singular beings with unique existence, but infinity suggests we are patterns, and patterns that repeat aren't unique. Some philosophers argue this isn't problematic. Identity is local. You are this instance of the pattern located here, experiencing this version of events. Other instances are them, located there, experiencing their versions. There's no confusion because the instances are spatially separated beyond any possibility of interaction. But this seems unsatisfying. If another version exists that's physically identical to you, having identical experiences and thoughts, in what sense are you distinct? What makes you you rather than them when there's no physical or experiential difference? You might appeal to location. You're the one here, they're the one there. But location in an infinite universe is arbitrary. There's no privileged position, no cosmic reference frame that distinguishes one location from another. You might appeal to history. You're the one with this specific causal history, they have a different history. But if the duplication is exact, you have identical histories. The causal chains that led to you and to your duplicate are equivalent even if spatially separated. The duplication problem gets worse when you consider variants. Not just exact duplicates, but near duplicates where small differences exist. Versions of you where one neuron fires differently. Versions where you made a different choice at some moment. Versions where history diverged slightly. In an infinite universe, all these variants exist. Every possible version of you compatible with physical law exists somewhere. You're not just duplicated, you're varied infinitely across possibility space. Which version is the real you? All of them? None of them? Is there a fact about which one you are? Or is you a more fluid concept than we intuitively believe? These questions intersect with the many worlds interpretation of quantum mechanics. If many worlds is correct, variants of you exist in different quantum branches. If the universe is also spatially infinite, variants exist in different spatial regions. The two sources of variation multiply, creating an even vaster ensemble of yous. Some physicists and philosophers embrace this, arguing that personal identity is indeed more fluid than intuition suggests. You're not a single entity, but a class of entities, all the versions across space and possibility that count as you according to some similarity metric. Others reject this dissolution of identity, insisting that consciousness is singular and unique, even if physical patterns repeat. There must be something, perhaps irreducibly subjective, that makes you this particular conscious experience rather than another physically identical one. But what could that something be? If consciousness emerges from physical processes, and those processes are identical in duplicates, how can conscious experience differ? What property could distinguish identical physical systems? This is where purely physical descriptions might fail. Maybe consciousness involves something beyond physical arrangements, some indexical property that makes each conscious experience unique, even when physical substrates are identical. Or maybe we need to revise our concept of identity entirely. Maybe individuals aren't the fundamental units of existence. Maybe the fundamental unit is the pattern, and what we call individuals are local instantiations of patterns that repeat throughout infinite space. In this view, death isn't the end of existence because the pattern continues in other instantiations. You continue to exist in your duplicates even after this particular instance ends. Identity becomes distributed across space and time rather than localized in one spatially contiguous body. This might sound like immortality, but it's a strange kind. You don't experience the continuation. From your perspective, death is still the end, but from a God's eye view, the pattern that constitutes you continues elsewhere. Is this comforting or terrifying? Does it make death less significant or identity less meaningful? Different people find different emotional resonances in these implications. The infinite duplication problem also affects moral reasoning. If every possible outcome of your choices occurs somewhere, do your choices matter? You might choose action A here, but somewhere else, a duplicate chooses action B. Both outcomes are realized. Does this make choice meaningless? Some argue yes, that in an infinite universe with all possibilities realized, individual decisions lose significance because the alternatives happen anyway. Others argue no, that your choices still matter locally. You determine which version of events occurs here in your causal region. Other regions are irrelevant because you can't interact with them. This mirrors debates about free will in a deterministic universe. If the future is determined, do choices matter? Most philosophers argue yes, that making choices and deliberating about them is part of how the deterministic process unfolds. Similarly, even if all choices are realized somewhere, making them here still matters. But the infinite case feels different. It's not just that one future is determined, it's that all futures are realized. The full space of possibility is actualized somewhere in the infinite universe. This creates a form of modal realism, the philosophical position that all possible worlds are real. Usually, modal realism is considered a metaphysical position about abstract possibility, but infinite universe scenarios make it physical. Possible worlds aren't abstract, they're concrete regions of space where different possibilities are actualized. The duplication problem isn't just philosophical, it affects how we think about observation and confirmation in cosmology. If every possible observation occurs infinitely often somewhere, how do we confirm theories? We observe that our region has particular properties, but in infinity, regions with different properties exist too. Our observations constrain what's possible in our region, but say nothing about the global universe. This returns to the measure problem. To make predictions in infinite universes, we need measures that specify which observations are typical versus atypical. But choosing measures is arbitrary, without empirical constraints. The infinite duplication problem is where the mathematical reality of infinity collides most directly with human intuitions about uniqueness and identity. We experience ourselves as unique individuals. Mathematics suggests we're endlessly replicated patterns. Reconciling these perspectives requires either revising our intuitions or questioning whether infinity is physically real. Despite measurements suggesting flatness, many cosmologists suspect the universe might actually be finite. Not because observations directly support finitude, but because infinity creates so many conceptual problems that finitude seems preferable if it can match observations. Several mechanisms could make the universe finite while appearing flat within our observable region. The most straightforward is topology. Space could be flat locally, but loop back on itself globally through topological identification. Imagine the universe as a giant three-dimensional donut, a torus. The surface of a torus can be flat, meaning angles in triangles sum to 180 degrees and parallel lines never meet. But the total space is finite because travelling far enough in any direction returns you to your starting point. Detecting such topology requires looking for repeating patterns. If space loops with period L, then light travelling distance L in any direction should show you the same objects from different angles. Galaxies would appear multiple times in different parts of the sky. Astronomers have searched for these patterns in galaxy surveys, and in the cosmic microwave background, they found nothing. Either the universe's topology has a scale much larger than the observable universe, or it simply isn't topologically connected in ways that create finite volume. If topology creates finiteness on scales exceeding the observable universe, then the universe is effectively infinite for us. We'll never detect the topology. We'll never see the repeating patterns. For all practical purposes, the universe might as well be infinite. Another possibility is that the universe is finite, but unbounded through positive curvature. If space curves positively enough, it closes on itself like a sphere's surface. The total volume would be finite, even though there are no edges or boundaries. Current measurements constrain curvature tightly. The universe is flat to within 0.4% according to Planck satellite data, but 0.4% isn't zero. There's room for small positive curvature that would make the universe finite. If the universe has the minimum curvature compatible with observations, its total size would be approximately 250 times the observable universe's diameter. That's large, roughly 23 trillion light-years across, but finite. A universe that size would contain approximately 10 to the power of 14 observable universe-sized regions. That's 100 trillion regions like ours, large enough that duplicates of Earth might exist, though the probability depends on details of structure formation. This finite but very large option avoids some infinity problems. There's no infinite duplication because configurations eventually stop repeating in finite space. The Boltzmann brane problem is mitigated because only finite time and finite volume are available for fluctuations. But it introduces new questions. Why is the universe flat to such high precision if it has curvature? The flatness problem returns. Inflation explains why the universe appears flat, but inflation typically predicts exactly flat, not almost flat, with tiny residual curvature. You'd need fine-tuned initial conditions or unusual inflation dynamics to produce a universe that's flat enough to match observations but curved enough to be finite. Not impossible, but requiring specific scenarios rather than generic predictions. A third option involves the universe having a boundary, not in space, but in its material content. Perhaps space extends infinitely, but contains only finite matter. Beyond some enormous distance, space exists, but it's truly empty, void of galaxies, dark matter, or any structure. This sounds ad hoc, but certain inflation models predict it. If inflation ended at different times in different regions, some regions would undergo more expansion than others. The regions where inflation ended early would form galaxies and structure. Regions where inflation continued longer would be stretched to near emptiness. In such scenarios, the observable universe sits in a finite island of matter, surrounded by infinite empty space. The universe is infinite spatially, but finite in content, avoiding duplication problems while matching flatness observations. Testing this requires detecting the edge of the matter distribution. If we could observe far enough to see galaxy density dropping to zero, we'd confirm finite matter content. But that edge, if it exists, lies far beyond our observable horizon. We can't observe it directly. We might detect it indirectly, through effects on the cosmic microwave background, or through gravitational influences on our local region. These searches are ongoing, but haven't yielded definitive results. There's also the possibility that our flat measurements are misleading. Perhaps some subtle systematic error in cosmic microwave background analysis biases curvature measurements towards zero. Perhaps the universe has significant curvature, but observational uncertainties hide it. This seems unlikely, given how thoroughly the data has been analysed and how consistent results are across different analysis methods. But science has been wrong before. Entrenched assumptions sometimes blind us to alternatives. Some cosmologists advocate for keeping an open mind. The measurements say flat, but flat has strange implications. Maybe we're measuring something slightly wrong or interpreting results through incorrect assumptions. There's precedent for this. Before the accelerating expansion was discovered, cosmologists assumed the expansion was decelerating. They interpreted observations through that lens until evidence became overwhelming that acceleration was real. Perhaps something similar could happen with the curvature. Another finite option involves reconsidering inflation. Standard inflation predicts flatness and likely generates an infinite universe through eternal inflation. But modified inflation models exist that avoid eternality and might produce finite universes. These models require specific fine-tuning or additional physics beyond standard inflation. They're less parsimonious than standard models, requiring extra assumptions, but they're not ruled out. If inflation was finite in duration and extent, the resulting universe could be finite. This depends on what caused inflation to end and what existed before it started. These are open questions in inflationary cosmology. Some theorists propose alternatives to inflation entirely. Perhaps the universe bounced from a previous contracting phase rather than beginning with a big bang. Perhaps it emerged from a quantum tunneling event that created finite initial volume. These alternatives are speculative and often face theoretical challenges, but they demonstrate that the standard picture isn't the only possibility. different initial conditions or different fundamental physics could produce finite universes compatible with current observations. The preference for finitude isn't just about avoiding mathematical problems. There's also an aesthetic preference rooted in physics history. Finite, comprehensible universes feel more scientifically tractable than infinite ones. In finite universes, you can, in principle, sum over all states, integrate over all regions, compute exact quantities. In infinite universes, you need limiting procedures, regularization schemes, measures that introduce ambiguity. Physics has historically favored theories that are mathematically clean and unambiguous. Infinity introduces ambiguity that makes some physicists uncomfortable. This discomfort motivates seeking finite alternatives even when observations point toward infinity. But discomfort isn't evidence. The universe might be infinite, regardless of our preferences. Nature doesn't care what's mathematically convenient for humans. If infinity is real, we must deal with it. The question of finite versus infinite can't be settled empirically if the distinction occurs at scales beyond observation. We can measure local curvature, but we can't directly measure global topology or total size. If the universe is finite, but much larger than observable, we'll never confirm finitude through direct observation. This makes the finite-infinite question partly empirical and partly metaphysical. The empirical part involves measuring curvature and searching for topological signatures. The metaphysical part involves judging which interpretation of ambiguous data is more plausible, given theoretical considerations. Reasonable physicists disagree on how to weight empirical versus theoretical considerations. Some prioritize observations and accept infinity if that's what measurements suggest. Others prioritize theoretical consistency and prefer finitude despite flatness measurements. This disagreement will likely persist until some new observation or theoretical breakthrough shifts the balance. Perhaps future quantum gravity theories will predict finite universes. Perhaps improved cosmological observations will detect non-zero curvature or topological signatures. Until then, the universe's total size remains uncertain. It might be infinite, as flatness suggests. It might be finite, but very large as alternative interpretations allow. We exist in one observable region, unable to determine the global truth. This uncertainty itself is illuminating. It shows the limits of empirical science. Some questions might be forever beyond direct observation, even though they concern physical reality. The universe's total size might be one such question, decidedly physical yet potentially unknowable. If the universe is infinite, containing all possible configurations, why do we observe this particular universe with its particular properties? Why these physical constants, these laws, this history? The anthropic principle offers an answer. We observe this universe because this is the type of universe that can contain observers like us. Universes with different properties wouldn't evolve life or consciousness, so nobody would be there to observe them. This sounds tautological at first. Obviously, we observe a universe compatible with our existence since we couldn't exist otherwise. But the principle has teeth when combined with infinity or multiverse scenarios. If infinitely many regions exist with different properties, most regions won't support life. The vast majority of possible parameter combinations produce sterile universes where stars don't form, chemistry doesn't work, or conditions are too extreme for complexity. But in infinity, even rare combinations occur somewhere, and observers only appear in those rare regions where conditions permit. So no matter how improbable our universe's properties, we shouldn't be surprised to find ourselves in such a universe because we couldn't find ourselves anywhere else. This explains what otherwise seems like remarkable fine-tuning. The fundamental constants of physics appear precisely calibrated to allow life. Change the electron mass by a few percent and chemistry breaks, alter the strong nuclear force slightly, and stars can't forge heavy elements, adjust the cosmological constant, and galaxies never form. These coincidences seem to demand explanation. Why are constants fine-tuned so precisely? In a single finite universe, the fine-tuning is mysterious. But in an infinite universe, or multiverse where constants vary across regions, fine-tuning is explained by observer selection. We exist in a fine-tuned region, not because the universe was designed for us, but because only fine-tuned regions can produce observers. We're in this type of region for the same reason fish find themselves in water rather than on land. It's not that nature prefers fish or water, it's that fish only survive where water exists. The anthropic principle shifts questions about why to questions about where. Not why are constants fine-tuned, but where do observers appear? The answer? In the rare regions where constants happen to permit observer formation. This is powerful if infinity or multiverse scenarios are correct. It explains fine-tuning without invoking design or fundamental necessity. The constants aren't special, our location is special, selected by the requirement that observers exist somewhere. But the anthropic principle has limitations and controversies. First, it's only explanatory if regions with different properties actually exist. In a single universe with fixed constants, anthropic reasoning explains nothing. It becomes relevant only given infinity or multiverse structure where constants vary. Second, it makes probabilistic predictions ambiguous. The principle says we should be typical observers, not exceptional ones. But defining typical requires a measure over all possible observers in all regions, and choosing that measure is arbitrary in infinite scenarios. For example, suppose some regions produce 1 billion observers, while others produce 1 trillion. Are we more likely to be in a 1 trillion observer region because more observers exist there? Or are both regions equally likely because they're both large? Different measures give different answers. This is another manifestation of the measure problem that plagues infinite cosmology. Without a principled way to choose measures, anthropic reasoning can't make definite predictions. Third, the anthropic principle is sometimes accused of being unfalsifiable. If any observation can be explained by claiming that's the type of universe where observers exist, then nothing can count as evidence against the principle. Defenders respond that the principle makes falsifiable predictions. It predicts we should observe parameters near the thresholds for observer formation, not deep in the life-permitting range. If we find constants extremely fine-tuned beyond what's minimally necessary, that would challenge anthropic explanations and suggest design or necessity instead. Some observations support this prediction. The cosmological constant is small but not zero, near the threshold where galaxies can form, but structures aren't too disrupted. If it were much smaller or larger by orders of magnitude, beyond necessary, anthropic reasoning would be strained. Other constants don't fit the pattern as clearly. Some appear more fine-tuned than anthropic reasoning suggests, leading to ongoing debates about whether anthropic explanations suffice. There's also controversy about what counts as an observer for anthropic purposes. Must observers be conscious? Must they be intelligent? Can simple self-replicating molecules count, or does observation require complex brains? Different answers lead to different predictions about which regions are observer compatible. This ambiguity makes testing anthropic hypotheses difficult because the hypothesis depends on definitions that aren't empirically determined. Despite controversies, many cosmologists take anthropic reasoning seriously as a tool for understanding apparent fine-tuning in infinite or multiverse scenarios. It provides a selection effect explanation that's more parsimonious than invoking purpose or fundamental necessity. The anthropic principle also connects to observer selection effects in surprising ways. If we're randomly selected from all observers in the universe, we should find ourselves in typical observer circumstances, not exceptional ones. This makes testable predictions. We shouldn't find ourselves in the first generation of observers if life will persist for billions more years, because most observers would exist later. We shouldn't find ourselves in an unusually empty or full region if typical regions have different densities. Testing these predictions requires estimating the distribution of observers across space and time. This is speculative, since we don't know how common life is or how long it persists. But the logic is sound. Typicality arguments constrain what we should observe if we're random samples from observer space. Some cosmologists have used anthropic reasoning to predict phenomena later confirmed by observation. Steven Weinberg used anthropic arguments in the 1980s to predict the cosmological constant should be small but non-zero, years before accelerating expansion was discovered. His reasoning: if the cosmological constant were much larger, galaxies couldn't form and observers wouldn't exist. The constant must be small enough for structure formation. This predicted a value in the range later observed, a success for anthropic reasoning. Skeptics argue this was lucky rather than truly predictive. The argument was loose and could have accommodated different outcomes. Only in retrospect does it look impressively predictive. Nonetheless, it demonstrates how anthropic reasoning can generate numerical predictions when combined with physics constraints. If we understand what conditions permit observers and how likely different regions are to have those conditions, we can predict what we should typically observe. The anthropic principle also raises deep questions about consciousness and observation. Why do conscious observers exist at all? The principle takes observer existence as given and asks what universes permit it, but it doesn't explain why consciousness arises or what role it plays in physics. Some interpretations of quantum mechanics give observers special status, suggesting observation or consciousness collapses wave functions and determines reality. If true, observers aren't just passive witnesses but active participants in creating reality. In such interpretations, anthropic reasoning becomes more profound. We don't just observe a universe compatible with our existence. Our observation participates in bringing that universe into existence from quantum possibilities. This ventures into speculative territory, where physics meets philosophy and possibly metaphysics. Most physicists remain agnostic about strong claims connecting consciousness to quantum mechanics, but minority views persist that take observation seriously as a physical process. Whether consciousness plays a special role or not, the anthropic principle highlights how observer selection affects what we can learn from observations. We're not impartial observers sampling randomly from all possible universes. We're selected observers existing only in regions compatible with our existence. This selection effect must be accounted for when reasoning from observations to conclusions about reality. Ignoring it can lead to false inferences, like concluding the universe is designed for life, when really life only exists where conditions permit. The anthropic principle doesn't resolve the infinity paradox. It doesn't tell us whether the universe is infinite or explain why we observe uniqueness despite possible infinite duplication. But it provides a framework for thinking about observer selection in infinite scenarios. If infinite regions exist, we should be unsurprised to find ourselves in an atypical region, because typical regions don't contain observers. Our existence selects for atypical conditions, and reasoning correctly about this selection is crucial for drawing valid conclusions from observations. Science operates on the principle that observations reveal universal truths. We study our local environment and extrapolate conclusions about reality more broadly. We assume that what we learn here applies there, that physical laws are universal, that knowledge gained from limited observations extends to unobserved realms. But infinity challenges this principle in fundamental ways. If the universe is infinite, and everything possible happens somewhere, then our observations might not reveal universal truths, but merely local accidents. Consider physical constants. We measure the electron mass, the speed of light, the strength of gravity. We treat these as fundamental constants that take the same values everywhere. But in an infinite multiverse where constants vary across regions, our measurements only determine local values. What we call physical constants might be environmental variables, properties of our particular region, rather than universal features of reality. Like measuring Earth's surface gravity and mistaking it for a universal constant when really it's specific to our planet's mass and radius. If constants vary, what remains truly constant? Perhaps only the equations or principles that determine how constants relate to each other. Perhaps the meta laws that govern which combinations of constants are possible across the multiverse. But this pushes fundamental physics one level deeper. We're no longer discovering the universe's laws, but the laws that govern possible universes. Science becomes a study of meta-laws, or landscapes of possibilities, rather than discovering the fundamental reality. This shift troubles some physicists. The goal of physics has been to find simple, elegant equations that explain everything we observe. Einstein dreamed of a unified theory that would reveal the deep underlying order of reality. But in an infinite multiverse, that dream might be misguided. There might be no simple explanation for why our universe has its specific properties. They might be environmental accidents, no more fundamental than Earth's temperature or atmospheric composition. Different regions have different properties for no deep reason beyond random variation. This would mean some questions physics asks have no answers. Why is the electron mass this value? Might be like asking, why is Everest this tall? It's this tall because of specific historical accidents in Earth's formation, not because of any deep principle requiring mountains of this height. If fundamental parameters are environmental, we can't hope to derive them from first principles. The best we can do is measure them locally and understand why observer selection picks out these values from the range of possibilities. This represents a retreat from physics' ambitions. Instead of explaining everything, we'd explain only the metastructure and accept that details are contingent. Some physicists find this unsatisfying, even depressing. Others see it as maturity, accepting limitations rather than pursuing impossible dreams. Infinity also affects how we confirm theories. Science advances by making predictions and testing them against observations. But in infinite universes where everything happens, how do we make predictions? Every possible observation occurs somewhere. If we predict observation A should occur, we're right because it occurs infinitely often. If we predict observation B shouldn't occur, we're wrong because it also occurs infinitely often. Predictions seem to lose meaning when all possibilities are realized. The solution involves probability and typicality. We don't predict A occurs and B doesn't. We predict A is more common than B, that random observers are more likely to see A than B. This requires defining probability measures over infinite sets, returning to the measure problem. Different choices of measure lead to different predictions. Without an agreed upon measure, theories can't make definite predictions. This creates ambiguity at the foundation of scientific methodology. Some view this as a crisis, suggesting infinity can't be physical. Others view it as a challenge, requiring new mathematical frameworks for reasoning about probability in infinite sets. The debate continues without resolution. Infinity might also limit what questions science can answer. In finite universes, we can ask about the whole universe's properties, its total size, total mass, average density. These are well-defined questions with definite answers. In infinite universes, global questions often become ill-defined. What's the total mass of an infinite universe? Infinity. What's the average density? Depends on how you take the limit. What's the most common galaxy type? Depends on the volume and sampling method. Questions that have straightforward answers in finite contexts become ambiguous in infinite ones. Science would have to restrict itself to local questions about observable regions, abandoning global questions as meaningless or unanswerable. This isn't necessarily problematic. Perhaps global questions aren't physically meaningful. Perhaps only local, observable properties matter for science. But it represents a significant shift in what kinds of knowledge we can expect science to provide. There's also the question of reproducibility. Science requires that experiments be reproducible, that other researchers can verify results by repeating measurements. But in infinite universes with varying properties, reproducibility becomes location dependent. An experiment conducted here gives certain results. The same experiment conducted in a region with different constants might give different results. Which result is correct? Both are, locally. But this means experimental results aren't universal, only representative of local conditions. We already accept this to some degree. Experiments on Earth might not reproduce in deep space where gravity and radiation differ. But those differences are understandable as environmental variations within a single universe with consistent laws. In an infinite multiverse with varying constants, the variations are more fundamental. The laws themselves differ, or at least the constants that appear in law equations. Reproducibility becomes contingent on being in similar regions rather than a universal feature of nature. Despite these challenges, science could continue functioning in infinite scenarios. We'd shift focus from discovering universal truths to mapping the landscape of possibilities and determining where we are within it. This is similar to how biology works. Biology doesn't seek simple universal laws like physics. It studies the complex contingent products of evolution. Different planets would have different biology, but biological principles like natural selection might still apply universally. In an infinite universe, physics might become more like biology. We'd study the specific physics of our region, while recognizing other regions have different physics. We'd seek meta-principles that explain the landscape of possibilities rather than deriving local properties from first principles. Some researchers have begun developing this landscape framework, particularly in string theory. String theory predicts a vast landscape of possible vacuum states, each corresponding to different physical constants. Our universe occupies one vacuum in this landscape. The landscape approach embraces the idea that many properties are environmental rather than fundamental. It shifts the goal from explaining why our universe has its specific properties to explaining the structure of possibility space and why observers exist in regions with our types of properties. Whether this approach succeeds remains controversial. Critics argue it's unfalsifiable, that it gives up on physics' goal of explaining observations from fundamental principles. Supporters argue it's realistic, accepting what observations and theory tell us, even if it requires revising expectations. Infinity also raises questions about the nature of scientific explanation. Traditionally, we explain phenomena by showing they follow from general laws. We explain planetary orbits by deriving them from gravity. We explain chemical bonding by deriving it from quantum mechanics. But if local properties are environmental accidents, this explanatory structure breaks down. We can't derive the electron mass from deeper principles if it's an environmental variable. The best we can do is explain why observers would find themselves in regions with electron masses in certain ranges. This is anthropic explanation rather than fundamental derivation. It explains observations through observer selection rather than through necessary consequences of fundamental laws. Whether this counts as genuine scientific explanation is debatable. Some philosophers argue anthropic reasoning is legitimate explanation. Others insist it's merely showing compatibility rather than truly explaining. The debate reflects deeper questions about what explanation means and what we should demand from scientific theories. Infinity might also affect how we think about theory choice and confirmation. Traditionally, we prefer simpler theories that explain more with less. Simplicity and parsimony guide theory selection when observations underdetermine which theory is correct, but in infinite scenarios, complexity might be inevitable. If reality consists of infinitely many regions with different properties, no simple theory will capture everything. Theories must be complex to accommodate the diversity. This doesn't mean abandoning simplicity as a criterion, but it might mean applying simplicity to meta-theories about the landscape, rather than to descriptions of specific regions. We'd seek simple principles that generate complex landscapes, rather than simple descriptions of the landscape itself. These shifts in how science operates would be profound. They'd affect methodology, epistemology, and the goals of scientific inquiry. Whether working scientists would adapt smoothly or face crises depends partly on how committed they are to traditional frameworks. Younger researchers entering fields without preconceptions about how science must work might adapt more easily than established scientists wedded to traditional paradigms. This generational dynamic has appeared before in scientific revolutions. Ultimately, if the universe is infinite, science would continue, but with revised expectations and methodologies. We'd still make observations, formulate theories, test predictions, but we'd interpret these activities differently, recognizing limitations and accepting ambiguities that finite universe assumptions could avoid. Whether this represents progress or retreat, acceptance of reality or abandonment of reason, depends on your perspective. What's clear is that infinity challenges fundamental assumptions about how science relates to reality. Not all cosmologists accept that the universe is infinite. Despite measurements suggesting flatness, several alternative frameworks could preserve finitude while matching observations. One alternative involves reconsidering what we mean by universe. Perhaps what we call the universe is actually just our local region, a bubble within a larger structure. The bubble could be finite even if the larger structure is infinite. This distinction appears in eternal inflation models. Inflation creates pocket universes, bubbles where inflation ends and normal expansion begins. Our observable universe sits within one such bubble. The bubble might be finite, bounded by regions still undergoing inflation. In this picture, the relevant question isn't whether space is infinite, but whether our bubble is infinite. The bubble could be finite, with a specific size determined by when and how inflation ended in our region. Measuring the bubble's size requires detecting its boundaries. If we could observe far enough to see where conditions transition from post-inflationary to inflationary, we'd determine the bubble size. But those boundaries, if they exist, lie beyond our current observational horizon. Another alternative questions whether space is fundamental. Perhaps space emerges from something more basic, and the emergent space could be finite, even if the underlying substrate is infinite or doesn't have spatial extent. This idea appears in quantum gravity approaches like loop quantum gravity and string theory. In these frameworks, space at the smallest scales isn't continuous, but discrete or emergent from more abstract structures. If space emerges, its global properties might depend on the emergence mechanism. Perhaps the mechanism naturally produces finite spatial extent, even when starting from principles that don't reference space at all. Testing emergent space scenarios requires quantum gravity observations, which are challenging because quantum effects are only significant at scales far smaller than we can probe. We need observations of the universe's earliest moments or of extreme environments like black hole interiors. A third alternative involves time rather than space. Perhaps the universe is finite in time, having a beginning and possibly an end, even if spatially infinite. The finiteness in time might constrain the implications of spatial infinity. In finite time, only finite possibilities are realized even in infinite space. There hasn't been time for all configurations to appear. Duplication remains possible, but not guaranteed. The Boltzmann brane problem is mitigated because fluctuations need time to occur. This temporal finitude could come from the universe's youth, only 13.8 billion years old, or from future evolution. If dark energy eventually causes a big rip or other cataclysm, the universe would have finite temporal extent, even if spatially infinite. Finite time doesn't fully solve infinity problems, but it makes them less acute. We're no longer dealing with infinite time infinities, but finite time infinities, which behave differently, mathematically and conceptually. Another alternative questions the cosmological principle itself. We assume the universe is statistically uniform on large scales, that matter distribution doesn't change systematically with distance. But what if this assumption is wrong? Perhaps our observable universe sits in an atypical region, denser or emptier than average. Perhaps density varies systematically, with distance in ways our limited observations haven't detected. If the universe isn't uniform, infinity doesn't imply infinite duplication. Testing uniformity requires observing very large scales across multiple directions. Current surveys reach hundreds of millions of light years, finding reasonable uniformity, but systematic variations could exist on larger scales. Some observations hint at possible non-uniformities: the axis of evil in the cosmic microwave background, large-scale flows of galaxies, and other anomalies might indicate departure from perfect uniformity. Most cosmologists think these are statistical flukes, but minority views persist. If the universe isn't uniform, all calculations about duplication and probability need revision. We can't simply extrapolate local properties to infinity. The global structure could be dramatically different from what local observations suggest. There's also the simulation hypothesis. Perhaps our universe is a simulation running on some computational substrate. Simulated universes could appear infinite to inhabitants, while actually being finite in terms of computational resources. This is highly speculative and arguably not testable scientifically, but it represents another way finitude could hide behind apparent infinity. The simulation could generate new regions on demand as observers approach them, creating the illusion of infinity while only computing finite amounts. The simulation idea is often dismissed as unfalsifiable metaphysics, but some researchers argue it makes testable predictions about computational limits or glitches that would reveal the simulation's finite nature. These searches haven't found anything conclusive. Another alternative involves reconsidering infinity itself. Mathematicians distinguish between different types of infinity: countable versus uncountable, potential versus actual. Perhaps the universe is infinite in some senses, but not others. For example, space might be potentially infinite, meaning you could always go further without finding an end, while being actually finite in the sense that the total volume is a finite number. This distinction matters philosophically, even if observationally indistinguishable. Or space might be countably infinite, consisting of discrete cells, versus uncountably infinite, like the real number continuum. Countable infinity has different properties and might avoid some paradoxes that plague uncountable infinity. These mathematical subtleties rarely enter popular discussions of cosmology, but they matter for rigorous treatments. Physicists should specify which type of infinity they mean and whether distinctions between types affect physical predictions. Some physicists advocate for finitism, the philosophical position that infinity doesn't exist physically. Infinities in our theories are idealizations or approximations, useful mathematically, but not corresponding to physical reality. In this view, when measurements suggest infinite space, we should interpret that as meaning very large finite space exceeding our measurement precision. The universe is always finite, but potentially larger than we can determine. Finitism is philosophically coherent and arguably more scientifically conservative than accepting actual infinity. But it's also somewhat arbitrary in where it draws limits. How large is large enough to count as effectively infinite versus actually finite? There are also alternatives that embrace infinity but avoid duplication. Perhaps physical laws are such that identical configurations are impossible even in infinite space. Perhaps some subtle quantum property prevents exact duplication, making every region unique despite infinity. This requires specific physics beyond current understanding. Quantum mechanics allows identical particles and configurations, so preventing duplication would need new principles. But such principles aren't ruled out. String theory provides one possible mechanism. In string theory, different regions might occupy different vacuum states with different physical constants. Even in infinite space, if every region has unique vacuum state, exact duplication could be avoided. Whether string theory actually predicts this depends on technical details still debated. Different vacuum states might have similar enough properties to create effective duplication, even if exact duplication is impossible. Finally, there's the possibility that we simply don't understand an infinity well enough to reason correctly about it. Perhaps mathematical infinity and physical infinity differ in ways we haven't grasped. Perhaps applying mathematical infinite reasoning to physical situations creates paradoxes because of misapplication. The question of whether the universe is infinite isn't just scientific, it's deeply philosophical, touching on existence, identity, meaning, and purpose. Start with existence. If the universe is infinite and everything possible exists somewhere, then existence becomes cheap. Anything that can exist does exist. There's no scarcity, no uniqueness, no special significance to any particular configuration of matter. You exist, but so do infinite copies and infinite variations. Your existence isn't special or unique. You're one instance of a pattern that repeats endlessly across infinity. Does this make existence meaningful or meaningless? Some find this liberating. If everything exists, then nothing is truly lost. Every possibility is realized. The full space of what could be is actualized somewhere. Existence achieves a kind of completeness in infinity. Others find it diminishing. If your existence is infinitely replicated, what makes you matter? Your choices don't determine outcomes uniquely, because all outcomes occur somewhere. Your life isn't special because infinite lives live out every variation. These reactions reflect deeper philosophical commitments about what makes existence meaningful. Is meaning found in uniqueness and rarity, or in participation in a complete actualization of possibilities? Consider death. In finite universes, death is the end of existence. You cease to be. But in infinite universes, with infinite copies, death is just the end of this instance. The pattern continues elsewhere. Other versions live on, experiencing futures you won't experience. Does this make death less significant? You don't continue in any experiential sense. From your perspective, death remains the end, but from a God's eye view, you persist in other instantiations. Some philosophers argue this provides a secular form of immortality, not personal continuation, but pattern continuation. Not you specifically persisting, but the you pattern persisting. Whether this provides comfort depends on what you value about existence. Personal identity becomes deeply puzzling in infinity. What makes you you? Not your physical composition, since that's duplicated infinitely. Not your memories, since copies have identical memories. Not your location, since location is arbitrary in infinite space. Perhaps you is not a singular entity, but a class, all the instances that count as you, according to some similarity metric. personal identity is distributed rather than localized. You are not one person, but many persons bound by similarity. This dissolves classical notions of identity. Instead of asking, "Am I identical to this past person?" we ask, "How similar am I to that past person?" Identity becomes gradational rather than binary. These philosophical shifts affect ethics. Traditional ethics assumes individuals are unique agents whose choices and experiences matter. But if individuals are duplicated infinitely and all choices are made by some version, how do we think about moral responsibility? One approach maintains that choices matter locally even if all outcomes occur globally. You still determine which outcome occurs in your causal region. Your moral responsibility is local, not global. Other regions are irrelevant because you can't affect them. This preserves moral reasoning while acknowledging infinity, but it requires accepting that ethics is fundamentally local, that there are no globally right actions, only locally appropriate ones given your situation. Another ethical question involves value. If everything possible exists, does anything have special value? Uniqueness often grounds value. Rare things are precious because they're rare, but nothing is rare in infinity. Everything that can exist does exist infinitely. Perhaps value comes from local perspective rather than global rarity. Things matter to you because of their relationship to your experiences and goals, not because they're cosmically unique. Value is agent relative rather than absolute. This shifts ethics from discovering objective values to constructing subjective ones. Not what is valuable, but what do I value? The universe doesn't provide answers. We create them through our perspectives and choices. The question of purpose also shifts. In finite universes, one might ask what the universe's purpose is, whether existence has a goal or direction. In infinite universes, where everything happens, purpose seems inapplicable. There's no goal because all goals are achieved somewhere. No purpose because all purposes are fulfilled in some region. The universe doesn't aim toward anything because it already contains everything. This might seem nihilistic, suggesting existence is purposeless. But alternatively, it could mean purpose is self-created rather than discovered. Since the universe doesn't impose purpose, we're free to create our own. Existentialists have long argued that humans must create meaning in a meaningless universe. Infinity might vindicate this view, showing that meaning is indeed self-created because no cosmic meaning exists to be discovered. Questions about free will also arise. If all choices are made by some version of you, in what sense are you free to choose? You can't make your choice the only choice, since other versions choose differently. Your freedom is only to determine which choice occurs here, not which choice occurs, period. This is similar to debates about determinism and free will. Determinists say the future is fixed, yet we can still be free in a compatibilist sense if our choices are part of how the future becomes fixed. Similarly, in infinity, all outcomes occur, yet we're free in determining which outcome occurs locally. Whether this preserves meaningful free will or shows freedom is illusory, depends on your conception of free will. If freedom requires genuine alternatives globally, infinity might eliminate it. If freedom only requires alternatives locally, infinity preserves it. The combination of infinity and quantum mechanics creates the most puzzling identity cases. If many worlds is correct and the universe is spatially infinite, you're distributed across both quantum branches and spatial regions. How many of you are there? The question might be ill-defined. You might not refer to a countable number of entities, but to a distribution across possibility space. Asking, "How many of me?" is like asking, "How many points are on a line?" The question assumes discreteness, where continuity might be more appropriate. Some philosophers embrace this dissolution of personal identity. The self is not a singular entity, but a distribution, a probability cloud over configuration space. We're not individuals in the traditional sense, but patterns with fuzzy boundaries and multiple instantiations. Others resist, insisting that consciousness is irreducibly first personal and singular. No matter how many physical copies exist, your conscious experience is uniquely yours, bound to this particular brain in this particular location. This debate connects to hard problems in philosophy of mind. What is consciousness? How does it relate to physical processes? Is it multiply realizable or unique to specific physical substrates? Infinity forces these questions into sharp focus. There's also the question of knowledge. If infinity makes many observations equally likely, how can we know anything? Our observations might be atypical, occurring in unusual regions that don't represent the whole. This skeptical worry exists for any observation, but infinity makes it more acute. In finite universes, we can appeal to laws of large numbers and typical cases. In infinite universes with ambiguous measures, typicality becomes unclear. Some philosophers argue this pushes toward pragmatism. We can't achieve certainty about global properties, but we can achieve practical knowledge sufficient for local action. Absolute truth might be beyond reach, but workable approximate truth suffices. The infinity question ultimately raises deep metaphysical issues about the nature of reality. Is reality fundamentally singular or plural? Does existence have intrinsic meaning, or is meaning imposed by conscious observers? Are individuals atomic units or emergent patterns? These questions lack empirical answers. Science can tell us whether the universe is infinite, but not whether infinity makes existence meaningful or meaningless, special or mundane. The empirical facts constrain philosophical conclusions, but don't determine them uniquely. Different people with different values and worldviews will draw different philosophical conclusions from the same empirical facts about infinity. This is appropriate because philosophy concerns values and meanings that science doesn't directly address. What matters is reasoning carefully about the implications, understanding how empirical claims about infinity connect to philosophical questions about meaning and value. The universe might be infinite, but what that means for human existence remains for us to determine. After exploring all angles of the infinity question, from measurements to mathematics to philosophy, we return to the uncomfortable truth. We don't know if the universe is infinite. Our best measurements suggest flatness implying infinity, but measurements have uncertainties. Interpretations involve assumptions. Alternatives exist that preserve finitude while matching observations. The question remains genuinely open despite confident claims from various sides. This uncertainty isn't weakness or failure. It's an honest acknowledgement of the limits of current knowledge. We've pushed observations as far as current technology allows. We've developed theoretical frameworks to interpret those observations, but we've reached a boundary where further progress requires either conceptual breakthroughs or dramatic improvements in observational capability. Perhaps future observations will resolve the question. Better measurements of cosmic microwave background might detect non-zero curvature, indicating finitude. Searches for topological signatures might find repeating patterns, proving the universe loops back on itself. Some unexpected phenomenon might reveal itself, providing new constraints. Or perhaps the question is forever beyond empirical resolution. If the distinction between finite and infinite occurs at scales exponentially exceeding the observable universe, no future observation will settle it. We'll remain uncertain whether our observable bubble is all that exists or whether it's one finite region in infinite space. Living with this uncertainty requires intellectual humility. We should hold our cosmological beliefs tentatively, acknowledging they might be wrong. The universe might surprise us, as it has before, when observations contradicted confident predictions. But uncertainty doesn't mean all positions are equally reasonable. Some interpretations of evidence are more plausible than others, given current knowledge. Flat space suggests infinity more strongly than finitude, even if certainty eludes us. We should proportion our confidence to the evidence, while remaining open to revision. Strong positions weakly held, as the saying goes. Confident enough to act on current understanding, but flexible enough to change when new information arrives. The practical implications of uncertainty are limited. Whether the universe is finite or infinite doesn't affect daily life or even most scientific research. Physics works the same way regardless. Technology develops identically. The question is intellectually fascinating, but practically inert. This might seem to make the question unimportant. If it doesn't affect anything practical, why care? But humans don't only care about practical matters. We care about understanding reality, about knowing our place in the cosmos, about grasping the universe's fundamental nature. The infinity question matters because it concerns the deepest possible questions about existence. Not just how things work, but what there is, how much of it exists, whether reality is finite or infinite in extent. These questions have captivated humans for millennia, and they remain captivating now. Moreover, the question connects to other issues that might have practical implications. The measure problem affects cosmological predictions. Observer selection influences how we interpret fine-tuning. The nature of personal identity relates to questions about consciousness and AI. Thinking carefully about infinity exercises philosophical muscles useful for other questions. It teaches us about the limits of science, about how to reason about the unobservable, about how empirical facts relate to philosophical interpretations. The uncertainty also teaches epistemic lessons. It shows how difficult it is to distinguish what we know from what we assume. Flatness measurements are secure, but their implications depend on assumptions about topology, about extrapolation, about interpretation frameworks. We often mistake interpretations for observations, treating theoretical conclusions as if they're empirical facts. The infinity question forces careful distinction between what's measured, what's inferred, what's assumed, and what's truly unknown. This careful epistemology is valuable beyond cosmology. In any field, distinguishing observations from interpretations matters. The infinity question provides an extreme case that makes these distinctions vivid and unavoidable. Living with uncertainty also means accepting that some questions might lack answers, at least answers accessible to us. Not every question has a solution. Some mysteries might be permanent features of reality rather than temporary gaps in knowledge. This acceptance isn't giving up or retreat. It's realism about human cognitive limits and observational boundaries. We're finite beings trying to understand potentially infinite reality using finite instruments and limited perspectives. Some questions might exceed our capacity regardless of how long we try. But accepting permanent mystery doesn't mean stopping inquiry. We should push as far as we can, extending knowledge to its limits, even if those limits don't encompass everything. The journey matters as much as the destination. The infinity question also highlights the amazing progress cosmology has made. A century ago, we didn't know other galaxies existed. Now we measure the universe's curvature to fractions of a percent and debate whether space extends infinitely. That's extraordinary progress, even if some questions remain unsettled. We've learned that the universe is vast, ancient, governed by comprehensible physical laws. We've traced its evolution from the first moments to the present. We've determined its composition, its expansion history, its large-scale structure. These are remarkable achievements, regardless of whether we've settled every question. Future generations might look back at our debates about infinity with answers we can't currently imagine. Or they might look back and think we were asking ill-posed questions, that the infinity issue dissolves when viewed from more advanced perspectives. Either way, the effort to understand matters. We're doing the best we can with available tools and concepts. That's all any generation can do. Progress comes from generations building on previous work, refining questions and developing better approaches. Perhaps the most important lesson from the infinity question is comfort with mystery. The universe is under no obligation to be comprehensible to humans. It might be stranger than we can imagine, operating by principles we can't grasp. That's okay. Mystery is part of existence. We can appreciate mystery while still seeking understanding. We can embrace uncertainty while still valuing knowledge. We can acknowledge limits while still pushing boundaries. These aren't contradictions, but complementary attitudes. The infinity question invites wonder. Whether finite or infinite, the universe is vast beyond ordinary comprehension. Contemplating cosmic scales, infinite duplication, eternal inflation, or any other aspect of modern cosmology evokes awe at the strangeness and grandeur of existence. That wonder is valuable for its own sake. Not everything needs practical application or definite answers. Sometimes the questions themselves are worthwhile, the pursuit itself is meaningful. The attempt to understand itself justifies the effort. If the universe is infinite, we're part of an endlessly repeating pattern, one instance among infinitely many, special only in our local context. If it's finite, we're unique, singular, the only version of ourselves that exists. Either possibility is profound. In infinity, we're diminished by lack of uniqueness, but expanded by participation in totality. Every possibility is realized. Nothing is lost. Existence achieves completeness. In finitude, we're unique and special, but existence is incomplete. Possibilities remain unrealized. Which is better? Neither, both. The question assumes value judgments that don't have objective answers. Reality is what it is regardless of our preferences. Learning to accept and appreciate reality as it is, whether finite or infinite, is part of intellectual and emotional maturity. The universe might be infinite, or it might be finite, but so large the distinction doesn't matter practically. Or it might be strange in ways we haven't considered, neither infinite nor finite, in traditional senses, but something else entirely. We don't know. We might never know with certainty, and that's okay. The question remains fascinating. The pursuit continues. The mystery persists. We exist in this moment, asking these questions, pushing toward understanding. Whether everything is everywhere, or whether we're unique, whether infinity is real or an idealization, whether duplicates exist beyond horizons or we're alone, these questions matter because we care about them, because they concern the deepest aspects of reality, because seeking truth is part of what makes us human. The universe is stranger than we imagine, and perhaps stranger than we can imagine. It might be infinite. The implications would be profound and disturbing. But profound and disturbing isn't the same as wrong. Reality owes us nothing. Truth isn't obligated to be comfortable. If the universe is infinite, why isn't everything everywhere? Because distance and cosmic horizons separate infinite copies beyond any possibility of interaction. Because infinity distributed across space doesn't mean uniformity at each point. Because mathematics, not intuition, guides us toward truth. Or perhaps the universe isn't infinite after all. Perhaps finitude hides behind apparent flatness. Perhaps alternatives we haven't imagined will emerge from future observations or theoretical breakthroughs. We live in the question, suspended between possibilities, uncertain yet curious, ignorant yet seeking, finite beings contemplating potential infinity. That's where we are. That's the human condition in the 21st century, standing at the edge of cosmic understanding, peering into mysteries that might never fully yield their secrets. And somehow that's exactly where we should be.